Good afternoon, everyone. Let's get started. Today we are going to talk about graphs. These are what we are going to talk about today. First of all, course logistics. Homework 9 is due next Tuesday, and homework 10, the last homework, will be out next Tuesday. And we will have one more lecture on graphs next Tuesday, and we will not cover dynamic programs and programming and other algorithm-related topics, and you'll learn about this in algorithms class. And on June 1st, we are going to have final exam review. And June 8th, we are going to have a final exam preparation day. So we are not going to have a lecture. And regarding final exam review, it is scheduled on June 1st, the lecture time, class time, and it's going to be online. And it is an optional lecture. As we did in midterm review session, it is going to be just Q&A session. And you can choose to attend the class or not. It is totally up to you. And we're not going to talk about new concepts or new problems. I'm just going to accept questions. And you can ask questions in Korean regarding lecture materials, and regarding homework problems, you can attend TA office hours. So questions regarding lecture materials, ask to me. And regarding homework problems, ask TAs. And regarding final exam, the schedule is not fixed, so it is just a tentative. It is going to be on June 13th from 1 p.m. to 3 p.m. And as we did in the midterm, it's going to be held in GS College Building C, room 104 and 109. And the coverage is from sorting to graphs. And you just need to have a look at lecture slides, the code I distributed, and homework problems. And homeworks are going to be from 6 to 10. And you don't have to study the optional problems, though I have not given you many optional homework problems in the last half of this course. And the format is going to be 2 types of problems, and total of 7 problems. I haven't yet made the final exam problems. Those are going to be similar to PPP exercises we handled during class. Basically, it's coding problems. And there are going to be some short answer questions. And as midterm, it's going to be closed book, closed laptop. So you need to bring your pen and eraser. Okay, that was about course logistics. Any questions regarding course logistics or final exam? Okay, there's no question. Let's move on. We're going to talk about disjoint sets first. Actually, we're going to solve the PPP exercise. This is where we left in the last class. So the problem was finding the earliest time when all the members get to know each other, or at least they are in the same social network. Okay, and the first thing we need to do is sorting these time steps. We want to check the earliest time step. So we are going to first sort these logs with timestamp. So we are going to use this key and lambda x 0. So this one is the key means we are going to sort the items inside these logs according to this criteria. And the criteria is going to be the first element, because the first element is the timestamp. And because we have three items inside each index, this sort algorithm does not know what to choose as a criteria for sorting. And we're just passing this parameter key and signify that the first element among these three items is going to be the criteria. So timestamp is going to be the criteria for sorting. And next, we're going to create a disjoint set. And because we have n number of people, we're going to make n disjoint sets. And we're going to count the number of groups. And initially, it's going to be n. Okay, so first, we're going to separately make disjoint sets for each person. And what we are going to do is, for each timestamp, we're going to have two people, friend A and friend B. And we can retrieve these three numbers or these three information from logs. So this one signifies the timestamp and the index of the first friend and the index of the second friend. And what we are going to do is, if these two friends are not connected in some way, what we are going to do is union these two friends. And then we're going to decrease the number of group count. And after we did this, if the number of group count becomes 1, that means we have just one group of people, meaning that all the people inside these logs are connected in some way. Then we just need to return the timestamp, because this is the earliest time when all the people get to know each other. And after we checked all the information inside these logs, and we have not reached the group count of 1, that means everyone cannot be connected. So we're going to just return -1. So this is the one solution, and there might be other solutions. So if you can pass all these test cases, then your solutions are also okay. Any questions about this problem? Okay, let's move on. So from now on, we're going to talk about graph traversals. What is graph traversals? Graph traveling means visiting all vertices inside a graph. And we do not visit the same node again. So for all nodes, we're going to visit each of them just once, no more than twice. And there are two major methods to visit all vertices in a graph. And the first one is called depth first search. And the second one is called breadth first search, and abbreviated as DFS and BFS. In fact, we talked about these two algorithms when we were talking about stacks and queues. What is the difference between DFS and BFS? In fact, we saw these when we were discussing stacks and queues. And this is the illustration of DFS and BFS. So what we are doing is we first start from this node and go to as far as we can go. So we go as far as we can go and we reach the end and come back and start visiting other nodes again. So it looks like the roots of some plant. However, in the case of BFS, we're just increasing the coverage one by one, like this. So we are increasing the coverage one by one, like this. So the configuration of DFS and BFS looks quite different. So it goes like this. However, BFS goes like this. So in Korean, it is called 응고선. I don't know how to call this in English, but anyway, these are how we perform DFS and BFS. Okay, let's implement DFS and BFS because we talked about it, talked about these two concepts in stacks and queues. So I guess we can implement these two concepts right away. All right. So from now on, we're going to talk about graph traversals. And the first thing we're going to talk about is DFS. By the way, I'll just show you some pseudocode, and you are going to implement the actual DFS and BFS solving PPP exercises. Okay. So first, we can implement DFS using recursion. So let's say we have G and V. Here, G signifies a graph, and V signifies the starting vertex. And let's say GV this one returns adjacent vertices of V. Okay, then how can you implement this one? First of all, we are going to check this vertex V is visited. So we're going to input feed true to visited V. And originally we need to have another list. This one is false times n. So we're going to check whether we visited this node or not. So these are some assumptions before we implement DFS using recursion. And after we mark that we visited this node V, starting node, what we are going to do is do something useful. So this means for each node, you need to do something like doubling the value of the node or getting the value of the node, things like that. To do whatever you want to do after you come to this node V. And after that, what we are going to do is for each neighbor in GV, so from our assumption, this returns the adjacent vertices of V. And for each node, each neighbor that is not visited, what we are going to do is call recursion of DFS like this. So this is basically how we implement the DFS using recursion. So pretty simple. However, sometimes we do not prefer recursion because that could cause Stack Overflow errors. And another way of implementing DFS is iteration. And for implementing DFS using iteration, we need to use a stack. So here, stack is just provided. And what we are going to do is we first initialize the stack with the starting vertex. And while the stack is not empty, what we are going to do is, let's say node. We're going to get one item from the stack. And if this node is not in visited, that means we need to process this node. And to visit it, we're going to append this node n, and we're going to visit n. Let's say we need to have visited like this. So this is another way of implementing visited. In the previous case, we just initialize all the nodes as false. However, in this case, we're starting from an empty node, empty list, and increasing this visited node as we visit other nodes. Okay. And then what we're going to do is to the stack, we're going to add the neighbor of this node B, except the visited node. So this is another way of implementing DFS using iteration. Okay, that was DFS. And from now on, we're going to talk about BFS. So because in the case of DFS, we're going as far as we can go using recursion. We end up visiting the node at the end, and then move to the next step and find the end from this node and reach 6, and then go back and search another endpoint. So this is why DFS is implemented in this way, using recursion or iteration. On the other hand, BFS is somewhat different. In the case of BFS, we are going to use Q to implement BFS. So here, Q is Q and V is starting vertex. What we are going to do is, first we are going to append V to our Q, and we're going to mark the starting vertex V as true because we visited, and we're going to visit V like this. And while our Q is not empty, what we are going to do is pop first element from Q. And for each neighbor in GV, if we have not visited this node, then we're going to append this node to our Q. And we're going to mark that W is visited. And then we're going to visit W like this. However, you don't have to visit W here. You can visit, you don't have to visit V here. You can visit here. So it doesn't really matter where you put visit. Okay, it's up to you. It's the different styles. And you can choose where to put visit. And another thing is you can also mark the visited status here rather than here. So it is up to you where to put visited or visit. All right. So that was BFS. And we use stacks to implement DFS. However, we use Q to implement BFS. Okay. So that was about BFS and DFS. And I'm going to give you one PPP exercise. And this PPP exercise, I'll also give you the full description of this problem. So this problem is about whether there is a valid path or not. So the valid path from source to destination. In this case, let's have a look at this first example. N signifies the number of vertices. So we have 6 vertices, and these edges signify the connection between 2 nodes. So 0 and 1 have one edge, and between 0 and 2 we have edge. And this source means the starting point, and destination is the end point. So we want to find whether there is a path we can reach starting from source to destination. If there is no valid path, no connection, then we're going to return false. Otherwise, we're going to return true. Okay? So these edges and N represent a graph. And what we want to do is check whether there is a valid path between source and destination in this graph. Take some time and try to implement this function. As usual, please send me PPP message before you try to solve this problem. I'll give it one more minute. Okay, let's solve this problem together. We can solve this problem in two ways. The first one is using DFS. However, before we move on, this format is not very easy to use, so we are going to somewhat change this format. Last class, we talked about adjacency list. So we are going to create adjacency list to represent this graph. So we have n number of edges, and we're going to store the adjacent vertices in this adjacency list. And for two nodes, what we're going to do is, to this adjacency list, we're going to update the 8th vertex as B as its neighbor, and B has A as its neighbor, because this graph is undirected. Okay. So this is the first step, converting this naive representation into somewhat more intuitive representation. In fact, this representation is more useful for implementing the rest of this function. And we're going to use stack here. We're going to initialize our stack with the source or the starting vertex. And we're going to make a visited set. And we're going to add the nodes we have visited to this visited set. However, as I told you, you can implement the visited as this list, like n that contains n false. And while this stack is not empty, we're going to first retrieve a node like this. And if this node is destination, then we're going to just return true. And if this node is in visited, then there's nothing we need to do more. So we're going to just pass this step. Otherwise, we are going to add this node to the visited set. And for neighbors of this node, adjacency list, and we're going to retrieve the neighbor of this node, the current node. And to the stack, we're going to append all neighbors like this. And after we process all the nodes, if we cannot reach the destination, then we're going to return false. So this is the first solution using DFS to solve this problem. And of course, there is another way of solving this problem using BFS. And we're going to do the same thing for BFS. We're going to make this adjacency list like this. And here, I would like to introduce one library. You can import collections, and these collections provide a QADT data structure called deck. So basically, you initialize this one with source. However, you can just use our list like this. And later on, we're going to just use top 0 like this. So they are basically the same. However, this one takes ON internally. However, these collections back provides O1 operation. So you better use Q from collections. Okay. And we're going to make visited as a set, and we're going to initialize this one with source. Oh, and while Q is not empty, what we're going to do is we're going to get one node from this queue, and pop 0, this one, becomes top left in the case of deck. And everything else is pretty much the same. We're going to check whether the current node is destination or not. And for each neighbor, we need to inspect our all neighbor in this adjacency list. We first need to check whether this neighbor is visited or not. If neighbor is not in visited, then we're going to add this neighbor to the visited set. And to the queue, we're going to append neighbor. And after we process all nodes, if you cannot reach the destination, we're going to return false. So basically, DFS and BFS look similar, but somewhat different. So if you just want to check whether there is a valid path or not, we can use both DFS and BFS. All right. By the way, I should have mentioned this before. However, the thing is, DFS and BFS are one of the most frequent topics that appear in coding interviews or coding tests of tech companies. And if you could solve this problem or the next problem, then I guess you can enter some big companies like Samsung or LG, because they give this kind of problems every year. Anyway, so that was a short brief information. And the second problem we're going to solve today is this one. I'll show you the picture. Okay, so this is our second problem. There was one question. What is the time complexity of DFS and BFS? Basically, we need to visit all the nodes. It's going to take ON to visit all the nodes. All right. So we don't usually think about the time complexity of BFS or DFS because we basically try to visit all the nodes. All right. And the second problem we are going to solve is this one. So we are going to get some grids that looks like this, 0, 1, 1, 0. that looks like this. And our purpose is starting from the left top, we want to go to bottom right. Okay. So from this position, we want to go to the bottom right, top left to the bottom right. And we can go in the diagonal direction. And to reach the destination from source, we need to pass two grids, this one and this one. And that is going to be the output of our function. I'll give you a second example. And in this case, we're going to receive this grid 0, 0, 0, 1, 1, 0, 1, 1, 0, like this. And from the top left position, we start here. And the only grids we can go is 0. So we cannot go in this direction or in this direction. We cannot go here and here. So we need to take the right direction at the first. And here we can go to this position because we can move diagonally. And then we can go down and can reach the destination. And to reach the destination, we need to pass 1, 2, 3, 4 edges, a node. So the answer is going to be 4. And in this case, if the first node is 1 here, then we cannot start from this node. That means we cannot reach the destination, and the answer is going to be -1. Okay, so our second PPP problem is given grid. We want to start from the top left and want to reach the bottom right. And the thing is, in this case, you cannot use either DFS or BFS. However, you just need to use one of them. So first, determine which one to use to solve this problem, DFS or BFS. And then try to implement this function. Please send me a PPP message before you tackle this problem as usual. And yeah, try hard to solve this problem because this one is very frequent in test coding interviews. I'll give you one more minute. Okay, let's solve this problem together. We need to use BFS in this case because what we want to do is finding the shortest path. And in this case, we're just increasing our coverage step by step. And as we increase our coverage, and once we reach the end, that means we don't have to increase our coverage any longer. And we find the minimum or the shortest path using BFS. However, in the DFS, it goes to the end, and we need to check all the endpoints and compare them. It's going to be less efficient than BFS when it comes to finding the shortest path. So we're going to use BFS for this problem. And to solve this problem, we're going to make a visited node like this. However, because this one is 2D grid, we need to make 2D visited array like this. So we need to make 2D visited grid that has the same shape as the input grid. And we are going to make a queue using deque. And to this queue, we are going to append the starting point like this. So this starting point signifies the x coordinate and y coordinate. And here, the last element represents the number of edges at the number of nodes we have visited. And because we are starting from the top left position, we have visited only one vertex or node. And another thing we're going to define is a dx and dy array. I'll explain this one after I show you how we define this dx and dy. So we are going to get some position x and y and add dx and dy to our current position. And this is going to be new x and new y. And here, the first one is 1 and 0. This means, let's say the current position is this position, and 1 and 0 means dx1 and dy0 means we are going downward. And in the y direction, we are not moving. So in this way, we can check all the neighbors. And in the case of less 1, -1 and 1, this means, let's say this one is the current position, then we're moving in the minus direction like this. And then in the y direction, we're moving upward, downward like this. So we're decreasing x1, increasing y1. So this one, the last element, means left bottom diagonal neighbor. All right. Once I implement this one, the meaning of dx and dy will be more clear. And while our Q is not empty, what we are going to do is retrieve these three numbers from our Q. And if the current grid is X and Y equals 1, then we cannot move to this position because we can only step on zeros. So we're just as this case. And if X is the length of grid minus 1, and if Y equals the length of grid 0 minus 1, then this means we have reached the bottom left, bottom right. So we're going to return D, this distance. Okay, we're keeping track of the distance. Otherwise, we're going to mark this X and Y position as visited. And for current X and current Y, what we are going to do is make new X and new Y like this. Okay, so by making this for loop simple, we can inspect all the neighbors. Otherwise, we need to make like nx1 equals x plus 1 and y1 equals y plus 0. And we need to make this kind of expression over and over to investigate all the neighbors. So by defining this dx and dy, we can make the process of inspecting all the neighbors very simple. And if this new nx is in the correct boundary, and y, ny is in the correct boundary, and if this grid nx and ny has the value of 0, and this one is not visited, then what we are going to do is append this position to our Q. However, we need to increase the distance by 1 because we are visiting one more node. And after inspecting all the possible cases, if we cannot reach the destination, then we're going to return -1. Okay, so this is very common problems if you are going to prepare for coding interviews or coding tests. Okay, up to this point, any questions? Cool, let's move on. From now on, we're going to talk about minimal spanning trees. First of all, what are minimal spanning trees? And we abbreviate minimal spanning trees as MST here. First, spanning trees is a connected subgraph in an undirected graph where all vertices are connected with the minimum number of edges. So in this example, we want to connect all nodes and if we connect A and B, so A and B are connected. If we connect A and C, A and D, and A and E, then all the nodes are connected, and we are using the minimum number of edges to connect all the components. However, you can also use these connections, A and E, A and B, B and C, C and D. This one also uses the same minimum number of edges and can successfully connect all the edges, all the vertices. So as you can see here, spanning trees are not unique. There can be multiple spanning trees. Okay, so undirected graph can have multiple spanning trees. Now let's talk about minimum spanning trees. Minimum spanning trees is a spanning tree with the minimum possible total edge weight in a weighted undirected graph. So what does it mean? In the previous case, the edges does not have any values. However, in the case of weighted undirected graph, edges have some values like this. And we want to find the minimum spanning tree that has the minimum possible total weight, edge weight. And we have many applications for MST. Let's say we want to visit some cities like A city, B city, C city, D city, E city. And we need to visit all these positions. Or you can think about 택배. You need to deliver some items. Then you want to move, saving all the possible resources. In those cases, you need to come up with the minimum possible total weight. And there are two algorithms to find minimum spanning trees. The first one is Kruskal's algorithm, and the second one is Prim's algorithm. And in this class, let's talk about Kruskal's algorithm first. The overall procedure is like this. We are going to sort all edges in the ascending order, and then add edges in that order into the MST. And we are going to skip some edges that will produce cycles. And repeat these two processes until we make n minus n edges are connected. So in this example, we have multiple edges. And this one signifies connecting 3 and 5, and the weight is 18. So we are sorting the edges before we perform Kruskal's algorithm. And what we do is choose the minimum edge one by one. We are going to choose 3, 5, 18, this edge first. And then the next step is 1, 2, because this one has the next minimum weight, 21. And we're going to choose 2, 6, this one. And 0, 2, this one. So we have chose this one, this one, this one, this one. And the next item we need to think about is 0, 1, which has 32, the weight of 32. However, if you choose this one, then this will create a cycle here. So we are just skipping this part and move on to the next one. Okay, so we are connecting these two nodes. And we're also skipping this one because it's going to create a cycle like this, 4 and 5. So we're skipping this one. And we choose the next one like this. So in this way, we can connect all the vertices using the minimum weight. So a pretty simple algorithm when you just look at this one using this figure. So let's implement this algorithm together. Kruskal's algorithm. Okay, we're going to implement Kruskal's algorithm. Okay. So as in the previous case, DFS and BFS, I'm going to just show you a pseudocode, and you're going to implement the actual cross-call algorithm in the PPP exercises. Let's say we're given a graph, and this graph has the form of vertex A and vertex B and weight, a set of these nodes, edges. And we're going to create a minimal spanning tree. And here we're going to use disjoint sets. And we're going to make n disjoint sets because we have n nodes. And we're going to sort the edges according to the weight. And the criteria is going to be this one, the weight. So we pass the criteria in this way. And MST cost is going to be 0 at the beginning. And while the length of MST is smaller than n-1, we retrieve 2 nodes and the weight. And we pop the first element from our nodes. And if these 2 nodes are not connected, we're going to union U and V. And then we're going to append U and V to our MST. And MST cost increases by val. So this is pretty simple, okay? And I'm going to give you the last PPP exercise of today. Okay, so this is our last exercise. We are going to implement minimum cost connections. So I'll just give you the description of this function. The input is some points, so 0, 0 to 0.2, 2, 3, 10. And what we want to find is the minimum distance to connect all these points. So here, this is the configuration of minimum weight. However, we're going to use not Euclidean distance. However, we are going to use Manhattan distance. So what is Manhattan distance? Let's think about these 2 points. The distance between these 2 points is, in the case of Manhattan distance, we go to the x direction 2 and then y direction. So the distance between these 2 points is 4. However, in the Euclidean distance, it's going to be √8. However, we are not using this Euclidean distance. And the distance between this point and this point is 5 plus 2. So we are using x direction and y direction to calculate the distance. All right. So we want to find the minimum weight to connect all these nodes, all these points. And solving this problem can be quite tricky. So I'll give you some hints here. And you can use this edge class to solve this problem. And it will ease the implementation. So have a look at these hints and try to use this edge class to solve this problem. In fact, we are running out of time, so this is going to be our final homework. And I will start from this point in the next class. So this is the end of today's class. If you have any questions, you can stay here. Otherwise, you can leave now.